Hello and welcome to section 3.5 on higher derivatives. The derivative of a function at a point indicates if the function is increasing or decreasing at that point. We can use this information to discuss the shape of a function's graph. In this section, we assume that the function f is differentiable on an interval. This means that the function is continuous along the interval. As a point p moves along the function in this interval, its instantaneous rate of change, the move that the point will make in the next instant, is described by the tangent line and the derivative at p. A positive derivative is associated with a tangent line with a positive slope, so the point will be increasing its y value the instant it moves to the right. The magnitude of this increase is directly related to the steepness of the tangent, however large the derivative will be. A negative derivative is associated with a tangent line with a negative slope, so the point will be decreasing its y value the instant it moves to the right. If the derivative is 0, the point's y value will remain unchanged at the instant it moves to the right. As the point moves to the right, tracing the function, decreases will happen when the red arrow points down, and increases will happen when the red arrow points up. We can graph the derivative function f prime on the same plane as the function f. Notice that the graph on the derivative crosses the x-axis precisely when the function has a horizontal tangent line. When the derivative function lies above the x-axis, the function f is increasing, and when the derivative function lies below the x-axis, the function f is decreasing. All of these observations hold for the derivative of the derivative, f double prime, the second derivative. When the second derivative is positive, the derivative function increases. When the second derivative is negative, the derivative function decreases. How does the second derivative f double prime affect the shape of the graph f? If the function is increasing and the second derivative is positive, then the function will curve slightly upward. This curving is called concavity. In this instance, the function is concave upwards. The tangent line indicates how the point will move in the next instant. If the second derivative is positive, then the derivative at the next instant will increase, and the rate at which the point rises will also increase. A function is concave upwards on intervals in which the second derivative is positive. A function is concave downwards on intervals in which the second derivative is negative. When the second derivative is 0, the function and the tangent line will be equal in the next instant. Here the derivative function f prime is constant. A curve is concave down if the curve lies below the tangent line of its points. A curve is concave up if the curve lies above the tangent lines of its points. When thinking of concavity, keep in mind that the top half of a circle is concave down, while the bottom half of a circle is concave up. In class, we will expand the definition of concavity and how the shape of a function's graph is determined by the first and second derivative. You've seen the basics. Now work towards mastery through practice and study.